Hey there, calc folks. Back here with what is going to be, I think, our last video here in the study of partial derivatives, folks, where we're going to look at the case for absolute extreme values of multivariable functions over closed regions. We are going to continue finish our study of partial derivatives here. With, again, a little bit more work with extreme values. But in this case, looking at that case of looking for absolute extreme values on closed regions, folks. Take note in the notes here and recall from Calc 1, folks, what was known as the extreme value theorem. All right? Remember what the extreme value theorem from Calc 1 told us, folks. It did tell us that if our function exists over some closed region in the domain, then we're going to be guaranteed to have both an absolute maximum and an absolute minimum value of the function on that region, right? In that region, you will have a location that will produce both an absolute maximum and an absolute minimum value for that function, if that function exists over some closed region. All right? Because it's over some closed region, you're not going to have it going off to infinities where it would negate the possibility of any absolute max or minimum value. Over a closed region, you're over a defined or a definite region of space where there is certainly always going to be an absolute maximum or an absolute minimum value in that space. All right? And what we note here is we are going to look at this case for the multivariable function z equal to f of x comma y. All right? And the way we are going to go about finding these absolute extreme values is very similar, or analogous, we would say, to the cases that we saw back in Calculus 1. And it's described in the following procedure here, folks. All right? We are going to start by assuming that we do have a continuous function, right, in our three-dimensional space over some closed region. This continuous function is equal to f of x comma y over this closed region. We are going to first determine the critical points within the closed region. All right? You're going to look within the region and find any critical points. You're then going to turn your attention to the bounds of the region and look for any critical points that might exist along the bounds of that region. Once you have your critical points within the region, and once you have the critical points on the bounds of the region, you're going to evaluate your function at these critical points. You're going to evaluate z equal to f of x comma y at the critical points found in part 1 and 2. And along with that, you're going to evaluate the function at any points of intersection in the bounds of these closed regions. All right? You're going to look where any bound happens to come together and intersect some other bound. There's a possibility at that point, right, where those two bounds intersect to be a critical value. So you're going to evaluate the function z also at those values. U8 z equal to f of x comma y at any point of intersection within those bounds. Right? And what you will then do is interpret. The largest value of f will be the absolute maximum value, and wherever that occurs at is where we would say it happens at in the domain. And the smallest value of f is going to be your absolute minimum value. And wherever it occurs at will be where that absolute minimum value occurs at in our domain, this closed region of space. All right. Let's look at an example. Consider the extreme values of 3x squared plus 2y squared minus 4y, this function, over region R in the domain of f defined here. Here we might say region R is defined as the set of coordinates in two-dimensional space such that the y values are between x squared and 4 in value. Y is always greater than or equal to x squared and at the same time less than or equal to 4. This is going to define a particular region in two-dimensional space over which our surface exists. This is the description of our closed region, folks. If we draw an illustration of that region, right, this would be the region's illustration, right? It would be this shaded region of space above the curve described by x squared and below the line where y equals 4. We are this region of space defined by these values of y. All right. Well, this surface, this region here we notice is a closed region. The surface forming over this region in the domain here, or in the xy plane, is going to illustrate both an absolute maximum and an absolute minimum value somewhere in that space. And what the directions tell us to look at is we do look at all the critical points that happen to lie in this region. We happen to look at any of the critical points that happen to lie along the bounds of this region. And we happen to look at any of these points of intersection, right, for these two bounds. We're going to look at the critical points, right, within this region, along the bounds of these regions, and we're going to look at these intersection points on our bounds. And we're going to say, well, what happens to f at each of those locations? Whatever is the largest value of f would be our absolute max. Whatever is the smallest value would be our absolute minimum value. All right? If we turn our attention to being within that region, we are going to look at the first partials. All right? And you notice if we look at the first partials of f with respect to x for this function, let me bring this down here. I don't like how this starts out. Note for this function, the critical points in R we'll say it this way. For the critical points in R, note the first partial with respect to x will just come from this term. That'll be 6x, and that equals 0 when x equals 0. And the first partial with respect to y for this function will be 4y minus 4. And 4y minus 4 equals 0 when y equals 0. All right? So in this region where we are going to expect to find a critical point is where those two events happen simultaneously, and that is going to be at the coordinate 0, 1. At 0, 1, x is equal to 0, and y is equal to 1. Right? That is where this event will be happening at the exact same time as this event will be happening. All right? That would be this location right there in our region. All right? That is going to be the critical point in that region. All right? That is the first one of the points we're going to analyze in our table here. We're going to look at f at that value here in a moment, in the end. We do have to look at all the critical points on those bounds now. And if we consider the bounds, this is the bound where y equals x squared. So if I consider y being x squared up here in this equation, you might note, as for the extreme values within the bounds of R and their corresponding critical points, note the bounds of R I really should say, as for the critical points within the bounds of R, note the bounds of R are defined by these bounds, y equals x squared and y equals 4, where if we go up to this equation here and we substitute in for yx squared, we will get our description of f in terms of just x being along that bound. And if we substitute in y equal to 4, we'll get that description of that bound in terms of strictly x. And we can analyze the first derivatives of f for the critical points along those bounds. Right. So the surface along the bounds, right, is defined by this equation to begin with, right? If we substitute in x squared for y, we will prepare f of x would then be equal to 2x to the fourth minus x squared, right? When y equals x squared. And f of x will end up equaling 3x squared plus 16 when y equals 4 in value. All right. Well, when do we see critical points for those values? Is when their first derivatives equal 0. Note the critical points along the bounds of f of x equal to 2x to the fourth minus x squared occur at x where f prime of x, which is this function seen here, 8x cubed minus 2x equals 0. Or when 2x times the quantity 4x squared minus 1 equals 0, or when x is equal to 0 coming from this factor and the zero product property, or when x equals plus or minus 1/2 coming from this factor and the zero product property. Right? These are going to be the locations for critical points along the bound described by y equals x squared. Right? Substituting in x of being plus or minus 1/2 into this equation, you will get a y value of 1/4 for both the positive and the negative case of x there. Substituting in 0, you will get 0. Right? Yielding then these critical points on this boundary. You will have the critical point at 0, 0, and you will have the critical points at plus or minus 1/2, 1/4 on this boundary. Whereas the critical points along the bounds of f of x equal to 3x squared plus 16, the case for being on the bound where y equals 4, right? These critical points occur when f prime of x equal to, in this case, 6x equals 0, which occurs when x equals 0, right? Yielding the critical point 0, 4 on this bound. Had to run a quick spell check on this. Anything you can tell, my difficult spelling words, yielding, I always misspell for some reason. I before E, Fred, I before E. Yielding, I just type, folks. It's the content. My brain is not thinking about spelling sometimes as I'm producing this content. Bear with me. So we end up with these critical points, folks. These critical points on our boundary: 0, 0, plus or minus 1/2, 1/4, and 0, 4. All right. Those are critical points on the boundaries. 1, 2, 3, 4 of those, plus the one within the boundary, 5. We're going to test those in the table, along with the bounds that occur at these intersections of these boundaries, at these points of intersection. One of those is going to be at negative 2, 4. The other one is going to be at 2, 4. Plus or minus 2, 4 will be these points of intersection. We're going to also want to test f at those values. We're going to want to evaluate f at those values. Right? I do think that is what I follow up with. Yeah. Evaluating z equal to f of x, y at these critical points and the intersection of these boundaries, the coordinates described by plus or minus 2, 4, produces the results seen in the following table. Right? Produces the results seen. Let's be a little more specific for what we're looking at is z of f of x, y in the following table. Right? At the critical point 0, 0, f is 0. At 0, 4, it's 16. At 1/2, 1/4, it's negative 1/8. At negative 1/2, 1/4, it's also negative 1/8. At 2, 4, it's 28. And negative 2, 4, it's 28. And at 0, 1, it is negative 2 in value. Now, how do we interpret these? The largest of these is where we're going to have an absolute max. So 28 is going to be an absolute maximum. And it does occur twice, well, at 2 locations, we might say. It occurs at the location 2, 4 and at the location negative 2, 4. Since it is the largest value in this table, it's going to be our absolute maximum, and it occurs at these 2 locations. As for the absolute minimum, that occurs at this critical point. And it is the value -2. The smallest value in the table is where we're going to expect to see our absolute minimum value. -2 is the smallest value, so that will be our absolute minimum, right? And it occurs at this coordinate 0, 1 within that region, right? That is interpreting absolute max and absolute minimum values, folks, right? And that is how we interpret them on a closed region. That's how we find those guaranteed values, right? I do make note of that here, respectively, right? Where we can actually look at the following illustration of this region, folks. Here is our surface, right? Here is our surface, where we're only interested in being on our surface in this closed region. And you can see I've highlighted that closed region on our surface here, right, in a different color. And what we have found, folks, is we have found that this location down here is the lowest point on that closed region in our surface. It's where we reach the bottom of that closed region at along the z-axis. That hits bottoms out at -2 along the z-axis, and that occurs at the coordinate 0, 1, respectively. All right? And you can kind of see the curvature there of the graph, how it behaves. That would be the low spot, right, passing through that region on the graph. Whereas the high spot, where does that occur? At these intersections, right? At these intersections on our boundaries, folks. You do have to look at the intersections on your boundaries. There is good potential for those intersections on the boundaries of these regions to be the high point on the region. And we see that is the case in this graph. We see those high spots occur at what? The value of 28 on the z-axis, right? So that is what we're finding here, folks. We are finding those values. Now, certainly there are other critical points on these boundaries. And this boundary seen here, right? But they are not absolute extreme values, right, on those bounds. Take note. All right? Folks, that is the procedure for finding absolute values on closed regions. When we have closed regions, you're guaranteed to have both an absolute max and an absolute minimum value on that region if it's closed. It could happen at a critical point within that region. It could happen at a critical point on the boundary of that region. Or it could happen at the intersections for the boundaries on that region. Right? And you find those critical points and you find those boundary locations, those intersections of the boundaries locations, and you evaluate f at all those locations. The largest value is your absolute max. The smallest value is your absolute minimum. All right. Folks, that ends my notes for this chapter 15 material. That ends our study of the partial derivative for this semester. We're going to be still looking at derivative. It's still going to be part of our notes. Chapter 17. We're still going to be looking at multivariable functions. Chapter 16. But we are going to be turning our focus to multiple integration, folks. Looking at performing integration with several iterations on a multivariable function. Yeah. And these videos you're going to see coming up are a little older in the sequence. I did prepare these last spring when we did go into, that remote learning situation that was presented to us at spring break last semester with the COVID folks that we're still dealing with. But before that, I did not have these videos prepared. I didn't really start making these videos until we went into that virtual mode. So the videos that we'll pick back up on the second half of this semester are actually chronologically recorded prior to this. point in time, folks. Right now, it's the 1st of October, or October 10th, 2020, folks. Those were recorded back during the month of April and May 2020. All right. Take note during the last 8 weeks of my spring 2020 semester. So they're going to have a little different feel to them. Right, take that all in as you start to get to those videos there. Do understand that. I might record a few, re-record a few of them. I don't know yet. Just time-wise, I'm a little overwhelmed with everything that I am having to do. But I do want to make sure that I do get you a complete lecture set, and this completes it, folks. This video here. I'll also try to get out a few more Mathematica demos, and then what I might be able to do here for the second half is do a little bit more Mathematica demoing. All right, having a little bit more time to do some of that with you. All right. But I hope you're doing well. Hope you're hanging in there. We're at about the halfway mark in our semester. All right, looking at this Calculus 3 material for most of you. All right. I hope these videos are helping. All right, folks. And like I said, there's a whole second half to the semester here waiting for you. All right, all ready to go. So you won't be waiting around for any more of these. They're there. All right. With that said, though, I'll see you in class this week, and I'll see you in the next videos, but it's not really true, right? Because those are really picking up somewhere else in time. But nonetheless, the material is the same. It's all presented very similar. It's all from my brain to the paper to the video. So, see you in the next one.